Welcome to day 24 of our journey through the standard template library. Today we are focusing on a class of algorithms that help us modify data in place. Powerful tools like copy, replace and remove, as well as their smarter counterparts, copy if, replace if and remove if. These aren't just utilities, they form the backbone of clean, efficient C++ code that works across containers with minimal boilerplate. Whether you are processing a dataset, transforming input, or filtering out unwanted entries, modifying algorithms can drastically simplify your workflow. Let's start by understanding what modifying algorithms are. In the STL, these algorithms operate not on containers directly, but on iterator ranges. That distinction is critical. They modify the elements within a range, like a segment of a vector or list, but they don't add or remove elements on their own. That means they won't change the container size, which is especially important to remember when you are using algorithms like remove. They work with various iterator types such as input, output, and forward iterators depending on the specific algorithm. In essence, modifying algorithms enable a functional, declarative approach to working with your data. You describe what you want to do, and STL takes care of the rest. std: copy is a basic yet powerful tool that lets you duplicate a range of elements from one container to another. It's commonly used when you want to replicate a dataset or apply filtering before operating on it. But sometimes you don't want to copy everything, just the items that classify a condition. That's where std: copy if comes in. Let's look at the code. We have a vector of integers from 1 to 5. First we copy all of them into another vector. Then using copy if, we only select the even numbers. The condition is specified using a lambda. In this case, x modulo 2 equals to 0. Note, if the target container does not have enough space allocated, you must use back inserter to safely append elements. Next up, we have replace and replace if. These algorithms are perfect for bulk transformations, changing every occurrence of a specific value or every value that meets a condition. For instance, suppose we want to replace every 2 in a vector with 10. Replace does this efficiently. But what if the rule is based on a condition, like replacing all values greater than 4 with 0? Then we turn to replace if, passing a predicate function that defines which values qualify. Again, these changes are made directly to the existing container, so be mindful if you are working with constant iterators or need to preserve the original data. Now let's tackle remove and remove if. These algorithms are slightly more nuanced. At first glance, they seem to delete elements from a container, but they don't. Instead, they rearrange the elements in place, pushing unwanted values to the end and returning an iterator to the new logical end. To truly erase these elements, we have to call .erase on the container using that returned iterator. For example, if we want to remove all 2's from a vector, remove helps reposition the remaining elements, then erase streams off the trail. The same applies to remove if, which uses a predicate. In this slide, we are removing all odd numbers from a vector. Again, first repositioning them with remove if, then erasing. This brings us to a fundamental STL pattern, the erase remove idiom. It's vital to remember that remove and remove if only shifts values. They don't actually reduce the container's size. The leftover elements at the end remain unless explicitly removed. So the full idiom is container.erase remove, container.end. This works beautifully with vector and dequeue, where random access and erase operations are cheap. You will find this pattern in most high quality C++ code bases. It's a sign of STL fluency. Let's apply this to a real-world example. Suppose you are preprocessing some input data that may contain invalid or unwanted values. Here we are working with a vector of integers. We want to remove all negative numbers and convert any zeros to ones. Using remove if, we eliminate the negatives. Then with replace, we transform the zeros. In just a few lines, the data is clean and ready for further processing. This is the power of STL modifying algorithms: expressive, composable, and efficient. Before you go wild with modifying algorithms, here are some best practices to follow. First, never forget the dot erase tab after using remove. Without it, your container will contain garbage at the end. Second, if your destination container does not already have enough space, use std: back inserter with copy or copy if. Otherwise, you will run into undefined behavior. Third, avoid overlapping ranges when using these algorithms. For instance, copying from a container into itself without caution can lead to subtle bugs. Lastly, chain your algorithms when possible. This leads to clean, declarative, and readable code. Let's quickly recap what we have covered today. Use copy and copy if when you want to duplicate or filter data into a new container. Use replace and replace if to transform values in place based either on equality or a condition. Use remove and remove if to filter out unwanted elements. But remember, you must follow it up with erase to truly remove them. All of this work on iterator ranges, not containers. So understanding iterator mechanics is key. Now it's your turn to get hands-on. Here are some practice problems to help you internalize today's concepts. Write a function that copies only prime numbers from one vector into another. Use replace if to convert all negative values in a list to their absolute values. Remove all elements divisible by 3 from a DQ using the erase remove idiom. And for a bonus, filter a list of strings to remove those with fewer than 5 characters. These exercises will cement your understanding of modifying algorithms and build your confidence in applying them in real code bases.